to talk about machine learning. I know, another machine learning video, another machine learning course, but this is going to be different because this is not about deep learning or neural networks or all of these technologies that are out there. This is about theory, proper statistical learning theory. The next couple of videos will be about this course, Foundations of Machine Learning, which was taught in Courant Institute by Professor Mohri, and we're going to discuss deep mathematical stuff in this course. So let's get started. We don't care about logistics. This is the textbook that goes with this course, and it is freely available on Professor Mohri's website. You can check this link. So this lecture is about basic definitions, concepts, introduction to the problem of learning, and some probability tools, which will be the core math which will be used in this course. So basic definition and concepts. What is machine learning? Computational methods using experience to improve performance. So these are some computational methods which use experience to improve performance, and we will somehow quantify what performance is. What is experience? Experience is something that is like a data-driven task. Thus, statistics, probability, and optimization. Like we have this computational method, and we give it more and more data, and it learns through the experience and improves performance. This is computer science because it is after all analysis of the algorithms, their complexity, and theoretical guarantees. So an example would be, let's say you use a document word count to predict its topic. You have a document and you scan through it and see what is its topic. It is a machine learning task. So a couple more examples would be text, document classification, spam detection, natural language processing tasks, speech, image, and face recognition, OCR. OCR is optical character recognition, handwriting recognition, games, chess, which has such a huge, action space, control of vehicles, robots, and medical diagnosis, fraud detection, network intrusion, stuff like this. These are all examples of learning tasks. Anyway, some broad ML tasks that we will be focusing on this course is classification, a big one. So classification is assign a category to each item, if it's 0 or 1 or 2, like classifier, if it's a mobile phone, or if it's a laptop, or if it's a table, or if it's a bookshelf. Regression is predict a real value for each item. So, for example, we have here prediction of stock values, economic variables. So what is the difference between classification and regression? For example, one can easily say that a regression is just like a classification, except it's a classification on a very continuous, very dense set, right? 1.1, 1.2, 1.3, 1.4, 1.5, all of them are different classification labels. However, there is a difference. In regression, we have an accurate metric on how far 1 is from 1.4. But in classification, we cannot say how far a mobile phone is from, let's say, an AirPods case. There's a difference. A mobile phone and AirPods case are two distinct classes, but 1 and 1.4 are 0.4 units away. So there is that difference if you keep that in mind. Ranking task is ordering items according to some criteria, relevant web pages, or let's say movie recommendations or anything. Clustering is you have some data and you want to find out regions where they are bunched up together. Like it could be used in geographical demographic analysis or any kind of thing. Dimensionality reduction is another machine learning task. It's very useful. You have a lot of data with a lot of fields, and in higher dimensions, everything is far away from each other. Like if you go in 100 dimensions, no 2 points are close to each other. So you need to reduce that dimension. I'm just talking advanced things, but the idea is that you need to reduce the complexity of the problem. And how do you reduce the complexity? You learn something really fundamental about the data, and then you can say that, all of these different features are not really useful. You only need to look at these couple features and their linear combination, and that's it. We have reduced the dimensionality of the problem. We'll get to it. So general objectives are what can be learned, under what conditions, can there be some guarantees, and how do you analyze learning algorithms? What can be learned? After all, you cannot learn random noise. If I give you a bunch of random noise and say that, oh, give me a model which learns this and predicts what's going to happen next, that cannot be learned. So on the algorithm side, more efficient and more accurate algorithms, something that deals with large scale problems and handles a variety of different learning problems. These are just some objectives. So this course is about theoretical foundation, the learning guarantees, and the analysis of algorithms. So the algorithms that we will discuss in this course are like mainly mathematically well-studied algorithms and discussions of their existence and their applications. So this is the key main idea, that we are discussing mathematically well-studied algorithms. We may not be discussing about neural networks because I don't know if they are well-studied, as well-studied as, let's say, support vector machines. So some topics that we'll get to is probability tools, which will be in this lecture, the pack learning model, Rademacher complexity, support vector machine, ensemble methods such as boosting, logistic regression, Maxent models, online learning, weighted majority, like online learning algorithms, regression, ranking, and reinforcement learning. All of this is coming up, and it's going to be a really exciting bunch of videos. So some definitions. An item. So what is an example? Example is an item, which is the instance of the data used. So for example, I gave you a bunch of images of this and call it, so that will be the example, a couple of images of me holding this AirPod case in different possible, orientations. That will be examples. What would be features? Features are attributes associated to an item, often represented as a vector. So an example is, let's say, a document, and the features would be, let's say, word counts, like itself, word counts, the number of times the appears, the number of times a appears, the number of times word appears, the number of times, let's say, sports appear, etc. Now what is a label? The label is a category for a classification task or a real value for a regression task. So I give a bunch of images of the AirPods, and the label would be that this is a black AirPods case. I give a couple of images of this, and then the label would be that this is an iPhone, etc. So this is the data. Data is the features, the example, and the labels. Training data. Test data is something that does not have labels, or maybe the labels are hidden from you. So what you're going to do then is use the training data, learn something, and then you have a system, you have an algorithm, and you're going to test it on something which has no labels. And then you'll be able to see how accurate that is with validation data. So validation data will be labeled, but the algorithm does not see it. So that way you know what the true label is, and then you can compare what the true label was and what the algorithm predicted. And that can be used to, fine tune some things. These are all just whatever, I'm sure you know this. So general learning scenarios are batch learning. What does batch learning mean? Batch learning means that the learner receives full training sample, let's say 1 million training samples, and then which the learner can read all of these 1 million training samples and then use it to predict, let's say, 100,000 other unseen points. What online learning means is that the algorithm receives one sample at a time. So let's say real-time data, for example. The algorithm receives one sample at a time and makes a prediction for that sample one at a time. And then maybe some oracle reveals that, oh, you made that mistake, or, oh, this was correct. And then the algorithm can go back and change some of these things. So these two are different things, and they are related too. We will get to it. So yeah, let's move on. So some standard batch scenarios are unsupervised learning. Unsupervised learning has no labeled data. So that means you are just given data, no labels, and you are supposed to learn something without even knowing what you are supposed to learn, which is crazy if you think about it. Supervised learning is, you have data, you have labels, and you learn data correspondence with the labels, and then finally you will be tested on data which does not have labels or unseen points. So that's supervised learning. What is semi-supervised learning? Semi-supervised learning uses both labeled and unlabeled data. So you can think of semi-supervised learning as something that, is more real world-esque. For example, you tell a child that, oh, this is a phone, That's a label, that's supervised. But then the child goes and looks at another glass and another piece of glass and says, oh, this is not a phone because that does not look like what I saw before. So that becomes unsupervised. So these are both combination, and we can call them semi-supervised learning. What is transduction? Transduction is like using labeled and unlabeled data for prediction on seen points. So semi-supervised learning, you predict on unseen points. Transduction, you predict on seen points. Whatever. So an example would be spam detection. So classify each email message as spam or non-spam. This is a binary classification problem. So potential data could be a large collection of spam and non-spam messages. So one would ask, how do you collect this data? And that's a good question, because significant human effort is put into labeling data. So example, you have like 1 million mails and you hire a bunch of people and they classify everything. Oh, this is spam, this is not spam, this is spam, this is not spam. So this is all, again, the input is coming from human data, at least for this problem. So this is the moreover like the flow chart of the learning. You have labeled data, you have training sample, validation data, and test sample, whatever. You have an algorithm, and you have some prior knowledge about what your algorithm or what your use case is. You are an expert in the field, so you have some prior knowledge, and that helps you decide features. What features are really key. Like features helps you decide what are the key variables that one needs to focus on when we are trying to do this, when you're trying to solve this problem. So the algorithm has some sets of parameters, and you learn it from the training sample, and you select the parameter based on the validation data, and then you evaluate on the test sample. It's whatever. The idea that I want to convey from this slide is that features are really important, and as an expert in the field, this can make or break your task. Like if you select really informative and dense features, you're golden. So introduction to the problem of learning. Now we are getting into the real stuff.
Which is RCN, and for Time Warner, which is now Spectrum.
So